Okay, so let's continue with continuity and with continuous function. So we talked about continuous functions and uniformly continuous functions. So I just remind you what was the definition, because it's kind of important to us and we are going to use that again. So I'm just gonna remind you one more time. So, well, we know what is the definition of a continuous function. We say a function f is continuous, but it's defined at a given point. So the point about continuity for a function is that it's always defined at a point, at a given point x. If for any positive epsilon, there exists a positive delta such that the following holds, such that if x prime is another point which is closer to x than delta, then the difference between f of x prime and f of x is less than epsilon. Okay, so this is the important definition. So the important thing is that it's defined at a given point, and at a point x. We have another definition. We say f is uniformly continuous being uniformly continuous is defined everywhere. So if for any positive epsilon, there exists a positive delta such that for any x and x prime, where x minus the absolute value of x minus x prime is less than delta, we have f of x minus f of x prime, or f of x prime minus f of x, its absolute value is less than epsilon. So the thing to note is that in the first definition, the definition depends on the point x. The important thing about the second one is that this definition is independent of the given point x. It should work for any x and x prime, which means here the delta we are going to choose, this number delta in the first definition, it depends on x. In the second definition, this delta should be independent of x. We saw one example. One thing we saw in the previous meeting was that being continuous or being uniformly continuous doesn't only depend on the function itself, it also depends on the domain of the function. So the example we saw was this one, y equals x squared. What we saw is that, of course, this function is continuous. But is it uniformly continuous or not? What we saw was, if we think about this function, y equals x squared, as a function from R to R, defined everywhere. If you take the domain to be the whole real line, it is not uniformly continuous. But if you think about the same function as a function from the interval 0 to 1 to the interval 0 to 1, on this interval, it is uniformly continuous. So it really depends on the domain which we define for. Here, there is something important about this domain. We can actually replace this domain with other domains, but there is something important about this one. For example, we can't prove it with, say, if instead of this domain, if we had, okay, so if it was 0 to, I don't know, 100, it still was correct. So the thing about these domains is that they have two properties. They're closed and they are bounded. Okay, so is there any question up to this point about the definition of continuity and uniformly continuous functions, and the fact that y equals x squared is continuous but not uniformly continuous? But if we restrict the domain to a closed bounded interval, it becomes uniformly continuous. Do you have any question up to this point? Okay, so let's continue. Okay, so y equals x squared, or y equals f of x for any function f. Suppose this function is continuous. Oops. I want to say we can show f as a function is uniformly continuous whenever we restrict the domain to an interval which is closed and bounded. So that's the claim. When f is continuous and when the interval, as you can see, is closed and bounded, then f is uniformly continuous. That's the theorem. That's a very important theorem. I want you to prove it, but just before that, there's a name for closed and bounded intervals, or closed and bounded subsets of Euclidean spaces. Does anyone know what do we call them? They are called compact subsets. We call them compact subsets of R. Okay, so I want you to prove this. I want you to show whenever f is continuous and whenever the domain is closed and bounded, the function is uniformly continuous. Okay, think about that for like 5 minutes and then I will tell you the answer. Okay, let me give you a hint. So we know f is continuous at every point x. But we want to show it is uniformly continuous. Let's prove it by a contradiction. So proof by contradiction. Suppose f restricted to the interval AB is not uniformly continuous. Therefore, well, we know what is the definition of being uniformly continuous. So if we negate that, it means there exists some positive epsilon such that doesn't matter what positive delta we choose, for any positive delta, we can find a point like x. We can find actually 2 points, x and x prime, where these 2 points, their difference is less than delta, but the difference between the values of the function f at these 2 points, f of x minus f of x prime, the absolute value, is not less than epsilon. So it means the function f is not uniformly continuous, right? Because being uniformly continuous means for any epsilon, there exists a delta such that whenever x and x prime, their difference, the absolute value of their difference is less than delta, then the absolute value of difference between f of x and f of x prime should be less than epsilon. So if we assume it's not uniformly continuous, we should negate this statement. Okay. So here we are saying for any delta, this thing happens. So it doesn't matter what delta we choose, this thing always will happen, right? So I'm going to choose some specific delta. So for example, I can choose delta to be 1, or I can choose delta to be 1/2, or I can take it to be 1/3, or in general, I can take delta n to be 1/n. For any of these numbers, this statement always holds. So doesn't matter which delta I choose, I can always find 2 points, x and x prime, such that they are closer to each other than delta, and the values of f at these 2 points, the difference is larger than epsilon. So when I choose delta n to be 1/n, actually this is a common theme in analysis in proofs. When we can choose any delta, we start to choose a sequence of numbers. So for example, 1, 1/2, 1/3, 1/4, etc. So we are taking delta n to be 1/n, and we end up with a sequence of numbers, because for each delta we get 2 points. For delta n, we get 2 points x and xn prime, such that the difference between xn and xn prime is less than delta, which is 1/n here. But still, as the statement says, f of x minus f of x prime is greater or equal than epsilon. Okay. Is it clear up to this point? Any question? Okay. Okay, I'm gonna erase the question itself. sorry, f of xn and f of xn prime. So I have two sequences of points here. One is xn, and the other one is xn prime. And both of these sequences are, the elements are coming from the interval, closed interval a, b. What can I say about the sequence in AB? These two sequences, of course, are bounded. And AB is a closed interval. It's a closed interval. What do I know about sequences which are bounded when they are inside a closed interval, closed bounded interval? Does anyone remember? What can I say about the sequence? It always has a supremum. That's correct. That's one way to put it. It always has a convergence subsequence. So maybe I can write it here as a statement. Any sequence inside a bounded closed interval has a convergent subsequence. It's a very important fact. We can prove it. It's not very hard to prove, but it's a very important thing to know. It's very, very, very useful. So you should remember this as a fact. This is a theorem. Okay. So xn, this sequence xn, has a subsequence. You're all familiar with the definition of a subsequence. It just means we can choose some of the elements of this sequence, infinitely many of the elements of the sequence in the increasing order in the in indices. So we usually show it with x and I. So it's a subsequence. Such that this subsequence is convergent. It converges to a point. I show this point with x. Okay, let me erase the rest. Okay, now look at the other sequence x and prime. Look at these indices we have here and I prime. Look at the terms in the other sequence which correspond to the same indices. So look at exactly x and I prime. So take exactly the same subsequence, the same indices, but from the other sequence of points from xn prime. The important thing is that this is still a sequence, not necessarily convergent. It's just a sequence inside this interval. But again, this interval is closed and bounded, and any sequence inside a closed and bounded interval has a convergent subsequence. So xn prime, x prime and I itself has a subsequence. Let's try it with x prime n I j, a subsequence which is convergent. So it's so say it converges to x prime. So we have two sequences now. One of them is converging to x, the other one is converging to x prime. So if I look at the same indices in these two different sequences, so x and ij and x and ij prime, these are two different sequences. One of them is convergent to x, the other one is convergent to x prime. We know that these elements of these two sequences, their difference is less than delta of this specific index, which is nij here. And we took this number to be 1 over n. And when n goes to infinity, this thing goes to 0. On the other hand, this is converging to x, the other one is converging to x prime. Therefore, the difference between x and x prime is going to 0, which means x is equal to x prime. Right? So x is equal to x prime. But remember what we said, we are going to prove by contradiction, right? We assumed f is not uniformly continuous. Remember what was the negate of that statement? What we had was this. I'm going to write it here. Although the negate was this, although the points are closer than delta, but they're f of x and ij minus f of x prime and ij is greater or equal than epsilon. Now, sending n to infinity, this is converging to f of x. This is converging to f of x prime because it's a continuous function, but x prime and x are equal. So this difference is actually 0, and it can't be greater or equal than a positive number. This is a contradiction. Therefore, well, we proved the theorem using proof by contradiction. Is it clear? Is there any question? This is not a very easy theorem, and it's quite important that when we have a continuous function, if the domain is closed and bounded, the function becomes uniformly continuous. And this is the way to prove this fact. Okay, so if there isn't any question, we can continue with the next question. Okay, now I want to, well, considering the things we are going to learn in future, I want to speak a little bit more about convex functions. Convex functions, so a function f is convex whenever it kind of looks like this. Either looks like this or looks like this or something like that. So the point is that these functions, they have a property that if we choose any 2 points, A and B, on the graph of the function, if we connect them with a line, with a straight line, a segment, this line is always above the graph of the function in the same area. So look at the graph of the function in the same area, like here. This segment is always above that. This is kind of the definition of a convex function. Or we can look at the other one. Say, take 2 points here, A and B. If I look at these points on the graph of the function, if I connect them, as you can see, this line is above this part of the graph of the function. Okay, this is called convex function. Now, what about this one? For example, is this Or, well, let me also add something. Either it's above the function or it's exactly the same as the function. So for example, this is also convex because if I choose any 2 points, because the line, because the segment which connects these 2 points is exactly the same as the function itself. So it's like greater or equal. So the line which connects any 2 points should be either on the function or it should be above the function. So these are some examples, and these are some examples of things which are not convex. So this is not a convex function. So this is convex. This is convex. This is convex. This is not a convex function because if I choose 2 points here, and say here, if I look at these points, the line which connects them is under the function. Actually, it is a concave function. Okay. Now, question, a nice question. Is this a convex function or not? This is not continuous. So there's a hole here, and at this point, the value of the function is defined to be another number. So assume this is 1. Suppose this is 2. Is this a convex function or not? Okay, you can tell me what you think. Is it convex? You can unmute yourself whenever you want and tell me what you think. Okay, can you explain more? So Kevin says it's not convex for all points. Can you elaborate? Mm-hmm. Okay, so yeah, you're right. So if we are supposed to choose 2 points, right? If I take one of the points to be this one and one of the points to be, say, this one, what happens is that the point on the graph above, say, A and B, those points, above A, the point on the graph is this point. And the point on the graph above B is this point. And if I connect them, this is what I'm going to get. And this is not above the function, right? So it's not convex. And it's pretty interesting because actually it's a thing. So here the function is not continuous at this point, right? And that's why it can't be convex. There's a theorem which I want you to think about it and prove it, that suppose f is convex, prove f is continuous. Okay, think about that for a few minutes. Why? What I'm saying is that this thing is kind of general. It's always the case. Whenever we have a point of discontinuity, just like this one, we can use that point to show the function is not convex. Oh, sorry, did you? Okay, I think for a second I got disconnected. Do you have the screen now? Okay, sorry. So, okay, so we are thinking we want to show f is continuous. So we are assuming f is convex and we want to show f is continuous. So suppose this is the function f. I want to draw the graph of f. Just before doing that, suppose I want to take any point x. So in order to show f is continuous, I should show f is continuous at every point x, right? So take a point x. I want to show f is continuous at every point x. So for example, this is x. I want to show f is continuous here. So look at f of x. So there is a value for the function at that point. It's just something, right? It's f of x. I want to show f is continuous around here, right? Look at two other points, say a and b, which one of them is on the left side of x, the other one is on the right side of the x, okay? So they have two values. Say this is f of a, and well, f of b is also something else. So this is f of b. Okay. Now there is something interesting. If I connect this point to the red point at a fa to the point above x, I would get a line. I know the graph of the function should be below that line, right? So the graph of the function should be somewhere here. The graph of the function can't be here. It is not possible for the graph of the function to be here, right? Okay. Now, on the other hand, well, let's look at picture of a convex function, a graph of a convex function. Whenever we connect 2 points, this line is above the function. But there is one more thing. It is always above the function between these 2 points, as you can see. But also, as you can see, it's always below the function after going, like if we are looking at 2 points A and B, when we are looking at the function on this interval A and B, this line is above the function. When we are looking at the points which are they're greater or equal than B, the graph of the function is above this line. And whenever we look at the points which are less than A, again, the graph of the function is above this line. And that's always a thing about the convex function. So if I look at these 2 points in here, if I look at these 2 points, A and X, if I connect them, the graph on this interval from A to X, the graph of the function should be below this line. But after, if I look at the points which are larger than X, so these points, the graph of the function should be above this line. So the graph of the function on this interval should be in this area. Does it make sense? Is it clear what I'm trying to say? So the graph of the function in the red, it should be in the red part. The graph of the function should be something here, for example, like that. And after X, the graph of the function should be something here. The graph of the function can't be here, and it can't be here. Okay, does it make sense? Any question? Okay. On the other hand, we can look at the points X and B. We have this point BF of B, and we have the point XFX. If I connect these 2 points, I would get another line. Again, because the function is convex, when I connect the point above X and B, above this interval XB, the function should be below this line. So the function should be here. The graph of the function should be here. And whenever I go outside of the interval XB, the function should be above this line. So the function should be, the graph of the function should be here. Now, look at the things we have. So look at the interval from A to X first. Look at this interval first. A to X. Once I argued using the points A and X, the graph of the function should be in the red area. And then using the points X and B, I argued the graph of the function should be in the blue area. Therefore, it should be in the intersection of these 2 points. So that the graph of the function actually should be in both of them, so it only can be here, in the black area. Now, look at the second interval, from X to B. Once I argued the graph of the function should be in the black area, and another time I argued the graph of the function should be in the blue area, it means the graph of the function should be in the intersection of these 2 areas, which I showed with green area. So I erase other lines. Whenever we take 3 points, the graph of the function, so whenever we take 3 points, A, X, B, we can connect A to X with a line and B to X with a line. And the graph of the function should always be inside this black and green area. So maybe, again, I show it on another graph. On a convex function, whenever we choose 3 points, A, X, and B, we can look at the values, the points above these 3 points. If we connect these points, if we connect A to X and X to B, if we look at this area between these two lines, that's where the graph of the function should be. It can't go outside of that. So the graph of the function should kind of be here, and from the other side, it should be here. What does it tell you? What does it tell you about the limits of f of x? And well, maybe it's better to show this point with x naughts rather than just x. When x converging is going to x naughts, it's kind of like the sandwich theorem. The limit has also, it has to be f of x naught, which means f is continuous there. So this image, this picture here, which forces f to be inside this yellow area, it makes the function continuous, because when the function comes closer and closer to the point x, it has to stay on this in this yellow area. So if it wants to be discontinuous, it should jump to some other point, right? But it's not allowed to go outside of this area. And using actually the kind of sandwich or whatever, I don't know what is the name actually. There are different names for it. This theorem shows the function has to converge to f of x. Okay. Is it clear? Is there any question? So there are two lines here. Both of these lines, when x is converging to x naught, both of these lines are converging to f of x naught. When an f is between these two lines, say L1 and L2. Say here, this is L2, this is L1. And both of these lines, they are converging to f of x naught when x goes to x naught. So f, since it's between them, f also has to converge to f of x naught, and that's by definition means it is continuous. Any question? Okay. Now, for the last, I think the last question in our document was this. Is there a continuous function f, such that f is not constant, but its derivative is 0 almost everywhere? What does it mean? What does almost everywhere mean? Because we have not read much, anything almost about measure theory. For us, it means on a set. Well, are you familiar with a set with measure 0? Or, well, we can say only on a, say, countable subset. So I'm asking, is there a function, say, from R to R, f, or from an interval, say, 0, 1 to R, the function f, which f is not constant, something like that. But outside a subset, say there is a subset A inside this interval, which this subset is very small. Say it is countable. Countable. Which outside of A, so on complement of A, f is differentiable and derivative of f is 0. But f is not constant. Do you know such a function, or can you prove if, so, you know, when we are looking at an interval and countable subset is a very small subset, right? There might be infinitely many elements, but countable subsets, we know the interval has uncountably many elements. So almost everywhere on the complement of these points, the derivative is 0. Does it imply f is constant or not? That's the question. Does anyone know the answer? Have you seen this question before? Okay, I want just to introduce this function to you. This is related to contour sets, the way we construct it. So the answer is yes, there is such a function. So the way to construct this function is like this. It's a good thing actually for you to think about more about it. It's an interesting thing actually. So look at the interval from 0 to 1. We can break this interval into 3 parts. 0 to 1 over 3, 1 over 3 to 2 over 3, and 2 over 3 to 1. So above this middle interval, I can make it red. Sorry. Above this interval, choose a value. Well, anything you want, say 1 over 2. And take the constant function above this interval. Look at the interval from 0 to 1 over 3. Break it into 3 parts. Do the same thing with the interval from 2 over 3 to 1. Above this interval, this interval starts from 1 over 9, I guess, to 2 over 9. Above this interval, fix the constant function 1 over 4. And here above this interval, the red interval there, again fix a constant function. Say 3 over 4. Now, there are some intervals left. Again, for example, look at the smallest interval, break that into 3 parts. Above the mid section, put a constant function. And break this interval from 2.9 to 1.3, break that and put a constant function there. And again, break the interval from 2 over 3 to, well, I don't know, this interval. Put a constant function there. And if we keep on continuing this process infinitely many times, we get something which is a function, which is, it ends up to be continuous. It's a very strange function. Let me erase this page and show you a picture of this function. Let me see if I can, well, wait for a second. Okay, look at this function here. This is what you're going to get if you continue infinitely many steps. And this function, although it doesn't look like it, but it's almost everywhere constant. So those points which it's jumping, there are only countable. And on the complement of that, this function is, the derivative of this function is 0. It's a very strange function. It's usually called Devil's staircase or contour function. And yeah, you can think about this function more. It's interesting for many different reasons. Maybe even looking at the Wikipedia page of this function would be interesting. Okay, that's it for today. Is there any question? Okay, try to stay safe. And you can email me any questions you have, because you're not on campus. It might be harder. You can just email me, or we can even like manage a Zoom meeting or whatever, whenever it's good for you. Okay, guys, have fun. Goodbye.